Hello and welcome again to the lecture course on Relativity and Cosmology Part 2. We are dealing with Chapter 9, the classic tests of relativity. And last time I derived for you the important perihelion motion of the planets, in particular Mercury. And we have seen that, in spite of, for two bodies, in spite of having an exact ellipse, we have a precessing ellipse. So there is an advance in the, say, perihelion, and in spite of the smallness of this effect, this has been observed and is one of the big successes of general relativity. So another big success we discussed today, which is the deflection of light. No? So in Newtonian physics, if you treat light just as a wave, not as a particle, as Newton himself did, there is no effect of gravity on light, but here in Einstein's theory there is. So light is attracted by masses, and for example, light ray that propagates in the vicinity of the sun is attracted by the mass of the sun. Now we continue with the formalism that we had before. So I showed you last time that for the orbit we have to evaluate this integral. So this is the polar angle, and the u is 1 over r. And w is an explicit expression that comes from the metric. And in case of light, we have to choose the constant capital K equals 0, if you recall from the variational principle of the geodesics. So that this W has a simpler form than for the planets. So we have here, if you look back, W squared of u is e to the mu minus nu f squared over L squared minus u squared. Yeah. So if you recall, in the last section, for the perihelion motion of Mercury, then there we had that this is e to the mu, e to the minus nu f squared minus 1. And so this here comes from k equals minus 1 minus u squared. So you see the difference between the two situations is more or less here seen in this term, and so this this minus 1 is lacking here. So we have to evaluate that integral for that simpler expression. Now recall last time we had also then not evaluated it exactly, although this is possible indirectly in terms of elliptical integrals, but we have made an expansion in terms of Schwarzschild radius over radius, because this is a very small quantity outside the sun, as I have shown you. So we do the same here. No? So we expand, so that's just a side remark, so we proceed here. So we expand this in terms of this power, and this is 1 plus beta 1 times g mu, and higher terms times 1 plus alpha 1 gmu plus higher terms f squared over L squared minus u squared. No? So that's from the e to the mu, and that's from the e to the minus nu. Of course, I should also take into account higher order terms in principle, and in the case of the perihelion motion we had done so, but as it turned out, and I take this now just for granted, as it turns out, this first linear approximation is sufficient for this effect. If one does not believe that, one just adds the next term, makes the expansion, and sees that the dominating contribution just comes from here. So I already take this here as given. So we have, and alpha 1 and beta 1 are these generalized parameters that can parameterize the effect so that we can see or can check the theory of relativity. Okay, so this here we can write as a term independent of u, which is just the f squared over L squared. So this comes just from here. Then we have here alpha 1 plus beta 1 gm s squared over L squared times u minus the u squared. No? So I collect all the linear terms here in u. So that's the alpha 1 term and the beta 1 term. And I neglect higher order terms. No? So that's okay, plus. And in the notation of last time, so I call this here the variable a, and this here in front of the u is the variable b. And okay, here we just have c is equal to 1. Yeah, so we had defined minus c times u squared, and if you have higher order terms, then c is not plus 1. For example, last time it was 1 plus gm squared, but this gm squared is not needed here, so the c is just equal to 1. No? So that's makes it simpler. Okay, and so we can insert this here, this expression, into the integral, so that we have here that this is integral to u, and I use here that I could also do it here, du tilde the square root of a plus b u tilde minus u tilde squared is the arc sine b minus 2u over square root of b squared plus 4a. Yeah, that's an elementary integral that you find in the table, or you have calculated it in your earlier years in the calculus lectures. Now, of course, we are interested in having radius in terms of angle, so we can invert that. So from this we have u, which recall is 1 over r, is b over 2 minus 1 half square root of b squared plus 4a sine phi. And okay, the b squared you see here is a term proportional to gm squared, which we neglect. So this here is of the order gm squared, and this is negligible. So that we have for this term is roughly 1/2 alpha 1 plus beta 1 gm f squared over L squared minus f over L sine phi. If we just insert here the b and neglect this term, then that's what we get. Now let me, when proceeding, choose the values for general relativity. So here, this term here, I take also this 1/2. So this here is in GR, the value 1/2. I mean, recall for GR we have here 2 and here 2. So this is just 2. No? But you can keep this and check with the observations whether it's consistent with GR or not. So from this you get then that u is f over L, and we have just slightly rewritten, f over L minus sine phi. Okay, so u has a dimension 1 over length because it's 1 over r. So this here, the dimension of f over L, and of course you know from this, the definition of this, that it has this dimension is 1 over length, so this is consistent. And so we can give this a name, so we can give f over L the name r to the minus 1. So this is a typical length scale of the problem, no? That is related to the parameters energy and angular momentum. So we have from here then that u of phi is r to the minus 1. So we have 2gm over r. And we have minus sine phi. Let me indicate this. So this is the expression we have to address. Now we are interested, of course, when r becomes minimal, the small r, which is the closest approach to the mass. This means that u becomes maximal, because u is 1 over r. So when does this become maximal? It becomes maximal if this here in blue is a plus 1. I mean, because this is the sign is between minus 1 and 1. So this becomes maximal, which means a minimal r for minus sine phi equal to 1. And of course, you know from elementary mathematics that this means phi is 3 pi over 2. And if we evaluate then u at this value, at this which gives a minimal radius, then we have r to the minus 1, which is 2gm over r plus 1. Now this here is a small quantity by assumption, so this is certainly negligible compared to 1. So we have here roughly r to the minus 1, so which means that this capital R has really the interpretation of being the minimal distance. So R minimal is R, or approximately even. Now let us look into a diagram. So I have prepared it here on that blackboard. So we have here the mass, and think about this as the sun. And we have here a light ray that comes from infinity, would propagate without the mass here. Of course, all of this is exaggerated in scale. No? But due to the mass, becomes here attracted and deflected and goes here. And so if you make the asymptotics here, then you would see that here there is a relative angle. And we call this the angle delta of the light deflection. That's how it is defined. And here this is the location of closest distance, which is our capital R, I mean to a high degree of accuracy. And this here is then some distance to some point, and here we neglect this this difference between the actual curve and here this horizontal curve. So the counting is we have phi equals 0. It's also here phi equals 0, and we count. We go here the mathematical positive sense counterclockwise. So that's here phi is 3 pi over 2. So that's the minimal distance that we discussed. No? So here, then this here is then 2 pi minus phi, and this is the same as this here, no? 2 pi minus phi, and we can consider this roughly as a triangle, neglecting the small difference. So this triangle here, which is this here, here has then that's a sine of 2 pi minus phi, is roughly r over r. The sine of this is then r over the small r, roughly, except for these tiny differences. Which means that, I mean, from this we then have that u, I mean the expression for u is given here, that u is approximately r to the minus 1 sine phi, which coincides with this expression here, as I said, for Schwarzschild radius much bigger than r. And this is really an extremely well fulfilled approximation, because for the Sun, the Schwarzschild radius is around 3 kilometers, and the radius of the Sun is 700,000 kilometers. So even if the light ray just touches the surface, I mean, you have a ratio of 10 to the minus 6 or so. So that's fulfilled. So here, asymptotically, we have r to infinity, which is u to 0, and so there we have phi. There phi is this very small angle delta over 2. So we get from what we had above. So recall we had u of phi is r to the minus 1 to gm over r minus sine phi. Now, so if we evaluate this now for u to 0, so asymptotically, then this becomes for u equals 0, this becomes then 2, okay, then this is equal to that, so 2 gm over r is sine phi, which means, and this is roughly phi, and so this is delta over 2. So we get then from this then the final relation. I mean, now this is what we desired. We wanted to have an expression for the deflection angle delta in terms of the m and r, the two parameters, no? the closest distance and the mass. So in terms of this, maybe I just write here, you have then delta is 4 gm over r, and if I allow myself to add a speed of light for illustration which was set equal to 1, then we have here the c squared. Now you see this is twice the Schwarzschild radius over the radius. So that's the expression that we get for the light deflection. So a very famous and important formula. So if you decided, or if you had decided to keep these two parameters alpha 1 and beta 1, you would have got the following term. Generally, we have here delta is alpha 1 plus beta 1 gm over r c squared. Now, and for general relativity, we have 2 plus 2, but if you had an alternative theory with different values for alpha 1 and beta 2, you would get a different result. Now, for the actual case of the Sun, which is the most massive body in the solar system, and if you have light rays close to the Sun, which numerical value do you get? And you can convince yourself by inserting here Schwarzschild radius of the Sun and say the radius of the Sun if the light ray just outside the Sun, and you get here then, so at the boundary of the Sun, you get delta, so approximately 1.75 arc seconds. Now this is again not an impressively large value. We are already used to small effects in general relativity, so the question is whether you can really observe that. But before telling you about that, let me mention the Newtonian approximation. Now, the Newtonian approximation, recall there we had a ds squared is minus e to the nu dt squared, and then we had here the unmodified flat space. No? There was only a modification here in the temporal part, then we had 1 plus twice the Newtonian potential over c squared. This means, I mean, that only this term has to be considered here in this expansion. So e to the mu would be 1, and we would only have this term. So we would have just then that e to the minus nu is then 1 plus alpha 1 times g mu and so on, and e to the mu would be 1. no? Which means that we only had here alpha 1, and from here beta 1 would be 0, and okay, alpha 1 would be 2. That is, in the Newtonian approximation, we only have half the result. So that is d Newton, delta Newton, which is alpha 1 plus beta 1 gm. Well, that's the general expression. But that would be then delta. So alpha 1 is 2 and beta 1 is 0. So this would be half the Einstein value. So you have a clear distinction between the Newtonian limit and general relativity. Or I should say really the Newtonian value, not just the limit, because the correct linear limit would lead here to a modification. Now, this half result was already found or predicted by Einstein in 1911, before he had his field equations, just from the equivalence principle. But the equivalence principle only sees this term. In fact, if you recall chapter 4, we had derived this Newtonian limit heuristically from the equivalence principle, and this only led to this. And in 1911, Einstein only had the equivalence principle, not the field equations. And he in fact predicted this value. And if you go to earlier literature, this value was already predicted by the German astronomer Soldner in 1801. Okay, how could this happen on the basis of Newtonian theory? Well, he calculated on the basis of the particle interpretation of light in the Newtonian theory. Now, Newton himself imagined light to consist of particles, and of course particles they feel gravity, and if you just calculate the deflection of a particle that comes with the speed of light near a massive body, then you get this result, delta over 2. I mean, this was before the wave theory of light was accepted with the experiments of Thomas Young and others, which were a couple of years later. So this is why this result was forgotten and probably not known to Einstein in 1911. Now, back to this observation or observability. This was done in a very famous historical mission named the Solar Eclipse Expedition of 1919. So at those days, I mean, to observe precisely a light ray of a star, say near the sun, was of course not possible because the sun is much too bright. So you have to wait for a total solar eclipse, so that the moon is in front of the sun and it becomes dark, you see the stars, and then you observe precisely the position of the stars. And then you took other photos from the same celestial region in the absence of the sun, and then you compare the difference compared to faraway stars, the relative distance. And from this, you infer then the value of light deflection. Now, there was the solar eclipse expedition of May 29, 1919. Actually consists of two missions. One led by Arthur Eddington, also had a general responsibility to the island of Principe. This is off the west coast of Africa and belonged to Portugal at the time. And the other led by Andrew Crommelin in Sobral in Brazil. And this is an interesting story. It has been told many times. You can find nice books on that. And there is some discussion about the size of the errors there, because the quality of the photographic plates were different. But within the errors, the two teams concluded that definitely the Einstein value was confirmed. And even if you think that those early result was still a little bit imprecise, of course later measurements and later observations confirmed this with much with a very small error. So here confirmed that delta is twice the Newtonian value. And this was also the time when the fame of Einstein for the general public started. So before he was, of course, known to the specialists, but from then on he was a public figure in the media, so an early media star, scientific media star. Now, of course, later solar eclipses were not so longer so favorable for that, because you have to wait for a solar eclipse. And starting from the 1960s with the discovery of quasars, you could observe, the radio waves from quasars near the sun, and you could observe them, okay, day and night in principle. Well, day, of course, when you see the sun, but you didn't have to wait for a solar eclipse. But still, people do that. So, the latest result was the eclipse of August 21, 2017. So one could observe this in the United States, and people in the United States did that. And you can find an article on that on the archive, and also on the publication 1802-00343. So you can read, about a very recent observation of this effect. This is more for, I would say, more for pleasure, because no one would have doubted anymore in this year that the Einstein is correct. But nevertheless, it's a good exercise to do that with modern equipment, and see how small the error is. This more or less finishes that. I would just say one word about another important application, and which we do not discuss here in detail. This is gravitational lensing. And perhaps in the advanced seminar in next autumn, perhaps we will accommodate a talk on that. What's gravitational lensing? This was an effect that was predicted by Einstein in 1936. Well, in fact, much earlier, but the publication is 1936, and observed since 1979. Okay, long after Einstein's death, but it's now an everyday tool for astronomers. So if you have in cosmology and in large-scale structure, if you have a mass distribution, say a galaxy cluster, and if you have a faraway object, a quasar, then of course the light from the quasar is deflected by that cluster in between, so it can go around here and around here. So if you look back, you see 2 or even more images of the quasar. Now that's what the gravitational lensing mean, and again this formula here plays a crucial role. So you can find many, impressive photographs on this in the internet of gravitational lensing from the Hubble Space Telescope and other satellites or telescopes. And this is a tool these days. It's not used as a test of relativity, of course. It's used as a tool to measure the universe. To have both the spatial and temporal, spatial distribution and temporal evolution of the universe, because these are cosmic distances, so you can probe, both the direct scale but also the evolution in time, as we will learn later when the universe expands. So you can use this to get information about the Hubble constant and about the space-time geometry and so on, about many other things, also about discovery of exoplanets and so on. So that's a field, a fascinating and still promising field of research by itself. And in this introductory course, I have no time to have to include a long discussion, but I mentioned this, emphasized this, and you will certainly learn about this in other occasions. So after having discussed light deflection, we now come to another effect that is different but still related, also concerning the motion of light in the vicinity of massive bodies. The situation is sketched here. So here we have the sun, here the Earth, and we have a planet, say Mercury or Venus, that can become or can move closer to the sun, and we envisage a light ray that we send from the Earth to the planet, or could be a radar, a radio signal, and reflected back here. And now if the sun is absent, it's clear that the effect is as in flat space-time. So we're interested in the time it takes to go to the planet and back. But if the sun is there, then we have the effect, of course, of gravitational time dilation. So we will have the effect that the light ray somehow wants to stay a little bit longer here in the gravitational field of the sun than it would be otherwise, and go back. So that's what we calculate, and it's named after the astrophysicist Shapiro, who also made in the 1960s the observations, and we call it the Shapiro time delay. Now the actual orbit is of course the one that we calculated in the last section, which is curved and which has the light deflection in it. But for the calculation here, we can assume that this is just a straight line, because the actual orbit deviates so little that it would constitute a higher order effect to the time delay. Now, we are not interested in the light deflection, we are only interested in the time delay. Now the starting point for this is again the isotropic form of the Schwarzschild metric. And in the linear approximation, so which is given by ds squared is minus 1 minus 2 gm over r dt squared, and then plus 1 plus, okay, and here again I can introduce a parameter. Two parameters are possible deviations from gr gm over r dx squared. No? So that's in the linear approximation where we have expanded to first order in the Schwarzschild radius over radius. So for gr, gamma is just 1. No? In our earlier notation, gamma is better 1 over 2, but we have only here this one parameter, and it's standard to call it gamma. Yeah, so I've already explained the diagram, and so it's in the z equals 0 plane, and we have here, I should say that's the minimal distance, which I call r0. And so let us calculate the time delay. Now the time delay we calculate, of course, from the metric, and recall that for light propagation, or generally null geodesics, we have ds squared equal to 0. So for the light propagation here, we take ds squared equal to 0. So if we call this G00, and then this here is then Gxx. So then we have here that G00 dt squared is approximately equal to minus Gxx dx squared, because in our situation we have dy and dz equal to 0. So it's only the x direction. And so we get from this that dx over dt is approximately plus or minus square root of minus G00 over Gxx. Okay, now we insert here the corresponding expressions. So we find then that we have then dt is approximately then plus or minus then square root, well, okay, first this here, 1 plus 2 gamma gm over r over 1 minus 2 gm over r dx, which we can expand as before, I mean the square root and also this denominator. So and if you do that, you find that this here, that the t squared is approximately plus or minus 1 plus 1 plus gamma. So that's the factor here from above, gm over r dx. No? So you see here that this one, actually this comes from the g00, but this gamma, this comes from gxx. No? So that's really in effect from space curvature. No? So this here is from space curvature, and not seen again in the Newtonian limit or the Newtonian physics. For gr, gamma is 1, and so for gr we have that the effect from the temporal part or temporal curvature is exactly equal to the effect of the spatial curvature. For other theories, this may be different. No, there are other theories of gravity where gamma is different from 1, so you have a different effect from space than you have from time. Now this r, because we have here quasi-Cartesian coordinates, I mean we can approximate this here, as I said, this curved line by the straight line. So this is why r is square root of x squared plus x naught squared. No? So any deviations from that, I mean this is r squared is x squared plus r naught squared. Any deviation from that can, r naught squared. Any deviation from that is negligible. Now we have to integrate this coordinate time now here from 0, which is the or we want to integrate from 0, which is the closest approach to the sun, to some value x, no, that we leave open. So we have then here a delta t of r and r naught, which we define as the integral from 0 to x, and we have 1 plus gamma gm over square root of x tilde squared plus r naught squared dx tilde. And this you can integrate exactly. So this here is x plus 1 plus gamma gm, the logarithm x plus square root x squared plus r naught squared over r naught, or you can also rewrite this logarithm in terms of the inverse of the hyperbolic sign. So that's also, I mean, the same as x plus 1 plus gamma gm area sinus hyperbolicus x over r naught. And this here, this additional term here, or this term is then called the time delay, or it gives the expression for the time delay, because that would be, I mean, for mass equals 0, this would be 0, and delta t equals to x is the flat space expression. We have set c equal to 1, so with speed of light we would just have here x over c is t. Now that's a flat space relation for light propagation, and this is modified here by, and it's prolonged by this term proportional to the mass. Yeah, let us go, let us set gamma equals to 1. which is the GR value. And then we get from this that delta t is x plus the 2 gm logarithm of x plus square root of x squared plus r naught squared over r naught, which, I mean, for r naught much smaller than x, which I will assume here. I mean, this means that later when we evaluate this here at the distance of the Earth, that this is much bigger than the distance to the Sun here. Otherwise, you just take the exact expression, x plus 2 gm and the logarithm 2x over r naught. Now, this is the coordinate time. Of course, what we measure here on our clocks is the proper time interval, and for that we must also take into account what we call the square root of the g00, I mean, which we get from the line element. I mean, this is the coordinate time, but for fixed x, I mean, this would be the proper time. So the proper time interval at r, at the distance r, is we call delta tau, depends on r and r naught, which is square root of the absolute value of g00 of r times delta t r and r naught. Now, this we have here calculated, and we have to consider this factor. So what we in fact do is we send a signal from the Earth to the planet and back, say a radar signal, passing as close as possible to the Sun, so that we can take this r naught approximately the radius of the Sun, and we neglect here for simplicity effects from the masses of the Sun and the planet, so that we can here have this here is approximately equal to square root of 1 minus 2 gm m Sun over Re, which is approximately 1 minus 2 minus gm solar mass over Re. So that's what we want to take, so that we have then here, then from this, that the delta tau Earth is, where we include a factor of 2 for the round trip, because it goes to the planet and back, and for symmetry that's just a factor of 2, so that's the round trip. And so then we have this factor 1 minus g m Sun over Re, and then we have here twice this term, so xe plus 1 plus gamma g m Sun, this xe over r Sun. So that's from Sun to Earth, and then we also have a corresponding expression for Sun planet. No? So we have here first this here, and then this here, and twice. No? So this here is Sun Earth, and then we have plus xp, and xp is in the diagram negative, so take the absolute value of this distance, plus 1 plus gamma gm Sun, and again this function. Yeah, no, so that's here planet, Sun planet. No? So you see, these are the results, and the only thing to be done is to insert numbers. Again, let me emphasize here, for general relativity, gamma is 1, so the two contributions from G00 and GXX, they coincide. So you can also, I mean, you have this time delay, but you could also give, instead of the time, just the corresponding spatial distance. So which would, I mean, a time delay would correspond to an apparent increase of the distance. So we can write that we have xe plus xp. So these are the two distances in flat space-time, and we have then some additional delta r from this logarithms or inverse hyperbolic signs instead of xe plus xp. No? So you could also just take this as a measure of the effect. And yeah, so this delta r from our expression is approximately g m sun 1 plus gamma, and you have these two contributions. So that's our result. And so if you make an observation, for example, with the planet Venus, and insert here the corresponding parameters, I mean the solar radius and also the distance of Venus and so on, then you find that delta r is approximately 60 kilometers. Yeah, if you set these two roughly equal to each other, of course Venus is a bit closer to the Sun, and if you set gamma equals to 1. So you see this effect, which is very small in terms of time, so it's more or less microseconds or so on, but it corresponds to that distance here, 60 kilometer, which you can imagine that have to be added here for the light propagation. And so the effect is the same roughly if you are in flat space-time and the light ray has to travel 60 kilometers more. The measurement, how do you do that? It's also very difficult, and you observe Mercury, say, and Venus. So you could compare this delta tau with the elapsed time in the absence of the Sun. Of course, you send signals to Venus in the absence of the Sun, but this is rather imprecise. So what the astronomers do is they measure the change of the proper time when, as viewed from our perspective, Venus approaches the sun, of course, it passes behind the Sun. So you make a differential measurement. And that is much more precise. And by now, it's not only done with Mercury and Venus. We also have various missions, like the Cassini missions to Saturn and its moons. And also we have the binary pulsars, and this Shapiro time delay has been measured there with very high accuracy. Now, so let me just give at the end the observations. So the original one for this factor 1/2 1 plus gamma, no, for GR this is just 1. And so it was found in two observations, 0.9 plus or minus 0.2, and or in another measurement 1.015 plus minus 0.05. So this was Shapiro, the original observations, and his collaborators in the years 1968 and 1971 with Mercury and Venus. And later there was the Viking mission, where a signal was sent to Mars and back, and also the Voyager 2 missions that were, going to Jupiter, Saturn, and so on. I do not write all of these, but let me mention the Cassini mission, 1 plus or minus 0.0000012. So this is the Cassini mission, which was a mission traveling to Saturn. And so these were results from 2003. So that, from these newer results, gamma minus 1, so the deviation of gamma from the general relativistic value was limited to roughly 1 in 100,000. So there's no issue of doubting, say, general relativity here. So, and these type of effects are no longer used to test relativity in the first place, but to use them to explore the universe. I mean, if you accept relativity and you measure these effects, you can get information, for example, about masses and distances. And and that's what astronomers are interested in. So that's all for today. I mean, these were two important effects. I mean, Shapiro effect is not, strictly speaking, a classic effect, because it was the measurements were in the 1960s, but still it's in the spirit of the classic tests. So we still will spend some time on effects in the Schwarzschild metric, and the next one would be so-called geodetic precession, that at least was calculated very early, but measurements were done later. The geodetic precision is when you know that a vector circling or vector moved around a mass will not return to its initial direction, and this you can do, of course, physically by a gyroscope orbiting, say, around the Earth, and you can measure that precession. So that is the next effect we calculate, and then we finally discuss one effect that goes a little bit beyond Schwarzschild metric, because we need rotation, and this is the Lense-Thirring effect. Thank you for today, and hope that you will watch me also next time.